Hi, my name is Kevin Backhouse and I'm a member of GitHub Security Lab. I'm very excited to participate in HITCON 2020. I'm just sad that I can't be there in person. Hopefully though I'll be able to get a chance to go to the conference at some stage in the future and meet some of you. Let me just quickly tell you a bit about myself. I'm a member of GitHub Security Lab. The image on the right shows the other lab members. The mission of the lab is open source software security. We do several things. We are a founding member of the Open Source Security Foundation. We are trying to build a community of security researchers who are helping to improve the security of open source. And we do our own security research looking for vulnerabilities in open source projects. I've been a security researcher since approximately 2017. Before that, I spent most of my career working on compilers. And recently, the thing that I've been focusing on is Ubuntu. Ubuntu is my favorite operating system, and so I'm keen to help make it as secure as possible. So I've been looking at the applications that are installed by default on Ubuntu, and one of those applications is going to be the focus of the talk today. Okay, so now I know it's traditional to, if you've got doing a talk about exploitation, to build up to the climax at the end where you show the video of the exploit running. But I'm going to do it the other way around, because I think if I show you the exploit running now, then that's going to help to give context to what I talk about in the rest of the talk. So I'm going to start an application that is installed by default on Ubuntu. This is Ubuntu 18.04, by the way. The exploit takes approximately 8 seconds to kick in. So there you go. There's the calculator that just popped up. Now, I'm going to show you that again. This time, what I'm going to show you is what's going on in the background. So let's start simple scan. And so in the background there, you can see some of the communication that's happening with the fake scanner. So what I've done is I've got another computer running on my home network that has got this server software that is pretending to be a network attached scanner. And so when simple scan starts scanning the network for network attached scanners, it gets malicious replies from this fake scanner, which then successfully gets code execution in simple scan. Now, most of the work involved in this exploit is in getting to this point that you see just here, where what you can see here is that it has received a remote info leak with values like the value of the stack canary and various addresses that allow it to determine the ASLR offsets. And that's actually the majority of the work in getting this exploit to work successfully, is getting to the point where we get that info leak. Once I've received the info leak, it's then actually really quite easy. I send back a response that contains a crafted ROP chain that overwrites the stack, and it gets code execution very quickly. So most of the work is in getting to this point, and that's what I'm going to be focusing on in this talk. So my plan for this exploit was to use it as a prank at work. Now, many of my colleagues are also have Ubuntu installed on their computers. Now, I doubt that many of them use simple scan on a regular basis, but I reckon I could have solved that with a little bit of social engineering. So I was going to send a message like this to our Slack channel. And because they're a helpful bunch, I bet a lot of my colleagues would have tried opening Simple Scanner up, and then I would have been able to pop calculators on their desktops, which would have been pretty fun. Unfortunately, due to COVID-19, we're all working from home right now, and so I didn't actually get a chance to try this out on my colleagues. Okay, so here's a quick overview of what I'm going to talk about for the rest of the presentation. So, first of all, I'm going to talk about the bugs that I exploited. They're in SANE, which stands for Scanner Access Now Easy. That's the library that's used under the hood in Simple Scanner to connect to the network attached scanners. So I'm going to show you those bugs. But actually, I don't think that's the most interesting part of this story. I think it would have been an awesome prank to be able to do that, run that exploit on my colleagues. But I think a genuine criminal probably wouldn't have found this exploit to be all that useful to them. So for me, the most interesting part of the story is about how, if you do have a bug like this, how you can then use glibc heap exploitation techniques to actually defeat ASLR and get code execution remotely. So after I've shown you the bugs, I'm going to talk about what the plan is for that exploit. And then I'm going to tell you a bit about some of the glibc heap exploitation techniques that I used. And then finally, I'll show you how I put those techniques together to complete the exploit. Okay, so these are the bugs. Now, you can see that there's quite a few, but the majority of these bugs, although they were security vulnerabilities, weren't useful to me as part of getting code execution in SANE. So they were just sort of remote denial of service type bugs. So there were two that were genuinely useful, which I'm going to show to you now. The first bug is a heap buffer overflow that I can trigger remotely in this function called epsons net read. So just notice here there's this variable called wanted. This function is going to read some data it's received off the network. And wanted is the amount of data that it's expecting to receive. And it is actually pre-allocated a buffer in order to receive that number of bytes. So if you scroll down here, then you can see that it's reading a header here from the incoming network data, and then it's reading a size value out of that header. And then this looks good here. It's checking that the size matches wanted. And so this is the case that you hit when you're talking to a legitimate scanner that's not trying to do something malicious. But then down here, it's got this other code where it says, well, what about if size is bigger than wanted? It still just goes ahead and reads all of that data into the pre-allocated buffer. And so this is a really powerful heap buffer overflow that we can use because we control the size of the overflow, and there's also no restrictions on what bytes we can write. So there's no restrictions along the lines of it can be only ASCII characters or something like that. We can write any bytes we want into the buffer. Now, there's one final thing that I want to show you about this little bit of code. I want you to just notice that there's a call to free here in this case. And now if we scroll down, in the final case, that's the case where size is less than wanted. Notice that there isn't a call to free in this code. And this is something that I find quite interesting because this turned out to be really useful. I mean, this is such a minor thing that it wouldn't even be classified as a security bug. I mean, all you're doing is leaking some memory because you forget to free it. But in fact, this turned out to be really useful to me when I was writing the exploit because what it allowed me to do was groom the heap by deliberately leaking lots of memory so that it would never get allocated again. And that way I could make sure that the memory allocation would happen from a contiguous sequence of addresses. Another thing that is similar to that is this code in E2 network discovery. So when you start up Simple Scanner, it immediately starts scanning the network for network attached scanners. And so the way that it does that is by sending out a UDP broadcast. And so what my fake scanner is doing is it's listening on port 3289 for this broadcast message. And when it receives it, it sends back not just one reply, but actually hundreds of replies. And what then happens is that this while loop here is written to handle the case where there's more than one scanner on the network. And so by sending back hundreds of replies, I can actually make this loop go round many, many times. And that's also really crucial for the exploit because it allows me to trigger the heap buffer overflow multiple times. If I hadn't been able to do that, I don't think there's any way that I could have got a working exploit because if I had to get code execution from the buffer overflow on the first attempt, I wouldn't know the ASLR offsets, and so I'd have no hope of actually having a successful exploit there. Okay, now let's look at the second bug. This bug is kind of a local info leak. So the bug here is that it's reading a number from an attacker-controlled incoming message. And then what it does is it allocates a buffer of that size, and then it copies into that buffer here, this memcopy. The problem is that it's forgotten to do a bounds check to make sure that it's not copying more bytes than there are actually in buff. And so what this allows me to do is read off the end of the buffer, and sometimes it's a buffer that's on the stack, and sometimes it's a buffer that's on the heap. I can read off the end of it and copy data that I shouldn't be able to read into a newly allocated buffer. The drawback of this bug is that although it's an info leak, the data that I've managed to obtain through this bug is on the wrong computer. It's on the victim's computer, not on the computer that my fake scanner is running on. And so in order to get that remote info leak, I'm going to have to do something else in order to get this info leak to actually help me get a remote info leak. Okay, so now what are some strategies for defeating ASLR? The most obvious one is brute force. Just try to guess the ASLR offsets until you're successful. On a 64-bit machine, this is pretty unrealistic. But what people sometimes do is they're able to, maybe by getting a partial info leak, maybe find out some of the bytes of the ASLR offsets, and thereby increase their chances of guessing correctly. So maybe you can get it, for example, down to a chance of 1 in 256 that you will actually guess correctly. And in some scenarios, that's actually a totally usable approach. But for me, that's not going to work, because my goal here is to have a prank that works first time. I mean, as soon as somebody starts up Simple Scanner, they immediately get code execution. So that's not going to work for me. Another possibility would be a remote info leak. So maybe you can find some bug whereby the program actually just sends you back all the data that you need, and you're ready to go with that. But that's kind of rare, and I certainly didn't find any bugs that were like that in SANE. The next possibility, and this is something that you see a lot in browser exploits, is if the program that you're trying to exploit contains a scripting engine, then you don't need a remote info leak. You can instead, if you just have a local info leak, similar to the one that I just showed you in SANE, then you can maybe just process that locally. I mean, usually the kind of thing that you need to do is a little bit of arithmetic on the ASLR offsets. You need to get the ASLR offset and then add something to it in order to deduce what the pointer to some important thing will be. And so if you've got a scripting engine in the victim program, then you can do that on site and you don't need to ship it off. Unfortunately, SANE doesn't contain a scripting engine, and so that wasn't a viable strategy for me either. And so the final possibility that I'm aware of for defeating ASLR is to manufacture an info leak. And so that's what I did in SANE. So let me show you the place in the code where I manufactured the info leak. So earlier we saw a function called epson's net read, and this is epson's net write. They actually work as a pair. So epson's net write sends out a message to the scanner, and it pre-allocates the buffer into which it expects to receive the reply, and then net read receives the reply and writes it into the buffer. And this function is the only place where data gets sent out over the network. And so if I want to manufacture an info leak, then I have to do it in this function. And so the strategy that I'm going to use is down here. You can see this is where it does the TCP write, where it sends out the data. What I want to do is I want to overwrite this variable buff size, make it much bigger than it should be, so that it sends out a lot more data than it ought to. And in the case where buff is a pointer to the stack, that means that I then get a a leak of lots of data off the stack, and that gives me all the information I need to then complete the exploit. The problem, though, is that buff size is actually stored in a register. So how am I going to use some kind of memory corruption vulnerability to change the value of something that's in a register? The answer to that is to do it during a function call. So back up here, this line that I've highlighted, you see there's a call to malloc. And during that call to malloc, buff size gets saved to the stack. And then after the call to malloc is finished, it gets loaded back off to the stack and put back into the register. And so if I can trigger a corruption of that specific stack address during the call to malloc, then I can turn buff size into a really big number, and then I get the remote info leak that I need. Okay, so here's a summary of that exploit plan. We're going to work backwards from the goal. So the goal is to overwrite buff size to trigger a remote info leak. The way that I'm going to do that is by writing garbage to the stack during the malloc. How do I trick malloc into writing garbage to the stack? Well, I do that by corrupting the heap's metadata so that during that call to malloc, it actually has that effect of overwriting the stack. But a really important step that I also need in order to be able to do that is I need to calculate the stack address that I want to overwrite. And so that's local info leak that I told you about earlier. What that does allow me to do is copy a stack address into a newly allocated heap buffer. But the stack address that I'm able to grab through that process is actually something like 300 bytes higher in memory than the stack address that I want to overwrite. So what I'm going to need to do is figure out a way to subtract that number, 300 bytes, from the stack address so that I have the correct stack pointer in order to set up this heap corruption in the malloc call. Okay, at this point I need to mention the Malloc Maleficarum. This is a legendary document from 2005 which introduced a number of these classic glibc heap exploitation techniques called things like the house of prime, the house of mind, and the house of force. The house of force is the technique that this talk is named after. Unfortunately, some of these techniques no longer work. Over the years, checks have been added to the malloc implementation to prevent some of these techniques from working. And that's the reason for the title of my talk, because unfortunately the house of force is going to no longer be a viable technique from glibc version 2.28 onwards. However, at the time that I was writing this exploit, the most kind of current version of Ubuntu, the most current long-term support version of Ubuntu, was 1804, and 1804 ships with glibc 2.27, and you can use the house of force on glibc 2.27. So this is kind of like last chance saloon to write an exploit that uses the house of force. The Malloc Maleficarum is named after this document called the Malleus Maleficarum, which is an exceptionally unpleasant document from the Middle Ages about witchcraft. The bit that I'm not quite sure about is where these house names came from. It's certainly not mentioned in the Wikipedia article. So I think maybe those names, like the House of Prime and so on, were actually invented by the author of Maleficarum rather than the Malleus Maleficarum. Okay, now if you want to learn about how to do glibc heap exploitation, then I really recommend this GitHub repository called How to Heap. This is how I learnt about glibc heap exploitation. What they've done here, it's really cool. They've taken all of those different techniques and they've enumerated them. So you can see that there's kind of a big long list of all the different techniques here. And for each one, they've created a little demo program that you can run in GDB, so you can step through and see exactly what's happening. So it's a really good way of explaining how all these different techniques work. And so I'm going to show you the House of Force demo from this How to Heap repository later on. Okay, quick refresher on glibc heap layout. The way that the allocator organizes data in the heap is it has bits of user data that have been given to the user through malloc calls, interspersed with bits of metadata. And the metadata contains things like the size of the chunk. And so let's just have a look at what that looks like in memory. So here's an example where we've got 4 chunks consecutive in memory. And so you can see here that there's a chunk of size 0x10. And if you then go 0x10 higher in memory, you get to chunk 1, which is also size 0x10. Now what I've done here is I've put in a chunk that's been freed. So the important difference here is that when you free a chunk, it starts also using the user data section as for metadata. And so what you can see here is that what previously had been the user data section of the chunk now contains 2 pointers, which are the forward and backwards pointer, because the chunk has been put into a doubly linked list. And so the important thing to be aware of when you're trying to do heap exploitation is that you need to make sure you don't overwrite these pointers of freed chunks, because if you do that, you're going to corrupt the metadata and you're probably going to crash the program. However, these sizes like the OX10, you can go ahead and overwrite those because they're not affected by ASLR offsets. So even when you're early in the early stages of an exploit and you haven't deduced the ASLR offsets yet, you can overwrite this metadata because it's all relative sizes. And then later on, once you've done something to actually deduce the ASLR offsets, at that point, that's when you can start overwriting these pointers in the heap metadata and maybe move to the next stage of your exploit by overwriting one of those pointers. And that's what's going to happen in my exploit too. Okay, so let's have a look at the house of force. The concept of the house of force is it's around the top chunk. So the top chunk is a special chunk that hasn't yet been allocated from. And so when the program tries to allocate some memory, then what the allocator will first do is it will first try to find a chunk that can be reused. It's got various caches that it can reuse chunks from. But if there's no more chunks left, if everything's already been used, then it needs to carve out a new bit of memory for you. And it does that by going to the top chunk and carving out some new memory from the top chunk. Now, the concept of the house of force is to use a vulnerability, something like a heap buffer overflow, to overwrite the metadata of the top chunk. And what it does is it makes the top chunk look like it's extremely big. So under normal circumstances, the top chunk would not be that big. I mean, probably no more than 0.5 megabyte. And if you ask for more memory than is available in the top chunk, then it will either try to ask the operating system whether it can make the top chunk bigger, or failing that, it will use an mmap to get some more memory from the operating system. But by overwriting the metadata, we make the allocator think that the top chunk is incredibly big, and so it will never ask the operating system for more memory. So let me show you the demo from the How to Heap repository of that. So this is the demo. Let's start it up. So if we step through this program a little bit, here they've allocated a 256 byte pointer. And because no allocations have happened yet, there's no cached chunks, and so this comes from the top chunk. So let's just have a quick look at what the memory looks like. If we go back OX10, then you can see the metadata of the chunk that was just allocated. And so you can see that the size of that chunk is OX110, OX10 extra for the metadata. And then if we go to the end of that chunk, you can see there, that's the top chunk. So that there is the size of the top chunk. So now what they're going to do is they're going to use a vulnerability to overwrite that. So the vulnerabilities happen now, and if we look at that memory again, you can see now that the size of the top chunk has become this huge number. And so then what they do, the way that they use this, is they calculate this evil size, which is actually a negative number, and then allocate a block of that size. And you can see that new pointer, the block that was just allocated, has come from where the top chunk was previously. But then the next allocation, so here we're going to allocate a new chunk here, and if you look at CTR chunk there and compare it to new pointer, you see that actually the memory address of CTR chunk is lower in memory than new pointer. So you can use this to get the allocator to return you a pointer to something that it really shouldn't have given you a pointer to. So you can then maybe do something like overwriting the stack with it. Okay. Now, I mentioned earlier that as part of the exploit, one of the things that I need to do is calculate a stack address. So I'm able to use that local infoleak to copy a stack pointer into a heap buffer, but then I need to subtract some offset from that, approximately 300 bytes from that, in order to get the stack address that I want to calculate. And I came up with the idea of using a variation on the House of Force to do this. So the idea is, rather than overwriting the size of the top chunk with just a huge number, I'm instead going to overwrite it with a pointer. And then I'm going to allocate a bit more memory and thereby shrink the top chunk slightly. And that will have the effect of subtracting an offset from that pointer which I'd written into the size of the top chunk. So that looks like this. You see there's a heap buffer overflow that's overwriting the top chunk. And so now there's a stack pointer in the top chunk. And then we allocate another chunk of memory, and that moves the top chunk up. And now the stack pointer has had that offset subtracted from it. So let me show you that. I have a demo of that, which is similar to the House of Force demo. So let's step through until we just allocated some memory. We've allocated OX800 of memory. And if we print this area of memory, so that's the size of the top chunk before anything happens. And now we're going to do the vulnerability. And so if I print the top chunk again, you can see now that I've overwritten the size of the top chunk with this pointer. And what we're going to do next is allocate OX1000. And so now if I print out where the top chunk was previously, you can see this is not the top chunk anymore because it's allocated a chunk of size OX1000. So the top chunk has moved upwards. And that's the top chunk now. And this is the same pointer that we wrote in before, but with an offset subtracted from it. And so then I can trigger that local info leak yet again in order to copy this pointer out of that memory and put it to where I need it in order to continue with the exploit. Okay, another technique that I use quite frequently during the exploit, and this is a relatively basic glibc heap exploitation technique, is just resizing chunks. So the idea is to use a heap buffer overflow to change the size of a chunk, and usually what you would use that to do is to make that resized chunk overlap with another chunk so that you can then corrupt some memory elsewhere. So it looks like this. So we're using a big heap buffer overflow. The buffer overflow starts in the first chunk, completely overwrites the second chunk, and then puts some fake metadata at the end of the second chunk. And so you can see now that it looks like that second chunk has grown, and then when you free it, it gets returned to the allocator looking like a different size than it was before. And so one of the things that I do with that during the course of the exploit is to create a chunk that overlaps with the top chunk. So the allocator is under the impression that there's one chunk that is here, and it doesn't realize that that chunk in fact has gone, is now overlapping with the top chunk. And so I can use that in conjunction with the local infoleak to grab that stack pointer and copy it into the metadata of the top chunk. Okay, so what I've shown you so far takes care of getting that stack pointer, subtracting an offset from it, and then copying it to somewhere where I can use it later. The next step of the exploit is to do something to overwrite the to actually trigger overwriting that stack address. So I knew that that was my goal. That's what I needed to do. So I started looking through the how to heap repository for some of these techniques, and to see if there was an existing technique that would do what I needed to do, which is during the call to malloc, write some garbage to the stack. By the way, something I just wanted to mention quickly. This is part of the reason that I'm very excited to be talking at HITCON. Because if you look through this how to heap repository, HITCON is mentioned numerous times. So I think the HITCON conference has often been at the forefront of developing new techniques for glibc heap exploitation. So one of the techniques that I found was this technique called unsorted bin attack. And it does almost exactly what I need. During a call to malloc, it writes garbage to an arbitrary address. The problem with this technique, though, was that it only works with large allocations. So you need to allocate more than 0x400 bytes in order to trigger this technique. And it turned out that the constraints of what I was working with in SANE meant that I had to trigger that overwrite during an allocation of 64 bytes. And so this technique wasn't going to work. So then I started looking around to see if I could find something similar that would have a similar effect but with a small allocation. And what I found was this code in the malloc implementation. The comment here kind of sums up what it's doing. If you've exhausted the contents of the tcache, which I'm going to explain to you in a second, then what it will do is it will then grab a chunk from the fastbin, which is another kind of cache. And what it will also do is it will replenish the tcache. And it's during that replenishing process, which is this while loop here, that I'm able to trigger that overwrite. So I'm going to show you some diagrams to show how this works. First of all, let me explain the tcache and the fastbin. So the fastbin has existed in the malloc implementation for much longer than the tcache. The tcache is a newer technique, and I kind of have the impression that the fast bins are obsolete at this point. That really the tcache has taken over as the main cache of the allocator, but the code for the fast bins is still there. So when you allocate some memory, and it's a small size, so 0x400 or less, then the very first thing the allocator does is it tries to see if there's an available chunk in the tcache. And the tcache is indexed by sizes. So if, for example, you try to allocate 64 bytes, then it will go to the slot for the 64-byte chunks and see if there's a chunk available for you. The tcache contains a maximum of 7 chunks per size, and that's going to be important later on in the technique that I'm going to show you. Okay, so if we ask for a chunk, then it takes it out of the tcache first. And it will do that until the tcache is empty. So allocate again comes from the tcache. Now, if we ask for another chunk to be allocated, then it comes from the fast bin because the tcache is empty. But then it doesn't just give you back a chunk from the fast bin. That code that I showed you earlier, the effect of that code is it will then try to refill the tcache from the fast bin. So all of these remaining chunks in the fast bin get moved over to the tcache. So that looks like this. Now, the important thing to notice is that this has had the side effect of reversing the list of chunks. And that reversing behavior is going to be quite important for the technique that I show you next. Okay, so the way that this technique works, and I've named the technique fastbin reverse into tcache, and I actually submitted a pull request against how to heap, which has been accepted. So this technique is now also part of the how to heap repository. And in fact, one of the maintainers told me that this technique, although they didn't have a demo in the how to heap repository, in fact, this technique was used as part of the HITCON CTF 2019. So what you have to do to get this to work is you have to set things up so that the tcache is empty and the fastbin contains at least 7 regular chunks, and then the final chunk in the sequence points to the address where you want to write some garbage. And the reason why you need to have 7 chunks here is so that it will stop copying when it gets to the stack address, because the stack address probably doesn't contain a valid next pointer, which is what I've indicated here by the little bomb symbol. So it's really important that the code doesn't try to dereference this invalid pointer, because if it does, then that will immediately crash the program. So that's why we need to have this exact number of chunks in the fastbin. So what we've done is we've used some kind of vulnerability to overwrite the pointer in G so that it contains a pointer to the stack address that we intend to overwrite. So what happens next is we allocate a chunk. So A goes down there into the allocated area, and then it starts copying these chunks across into the tcache. So B, C, D, E, F, G, and then it thinks that the stack pointer is another chunk, and so it copies that across into the tcache. Now, what's happened here is that it's written a pointer to G into that stack address. So this has now achieved the effect that we want, which is to write a garbage value onto the stack, or a very big number has been written onto the stack. Now, important thing to notice here is that the fastbin now points to an invalid pointer. And so it's really important that at this point we complete the exploit quickly, because we're in a very fragile state where if anybody tries to allocate another chunk of memory from the fastbin, then the program's going to crash. So we've got to get the exploit working quickly now. But I got really lucky here, or I feel like I got really lucky, because if you allocate one more chunk, then what happens is you get back that stack pointer. And so this actually was really convenient for me when I was writing the exploit, because what I'm able to do is, after I've received the remote info leak, I can then send back a crafted buffer, which, because of this behavior that the next allocation goes on the stack, that buffer that I send back actually gets written to the stack. And so I've just received the info leak containing the stack canary and everything. I'm able to craft a buffer of memory that gets sent back, written onto the stack, and then I'm able to get code execution very easily from that. Okay, so it's time to complete the exploit. This is still a little bit of a simplification of everything that happens during the exploit, but these are the major steps. So step 1 is to groom the heap. And so that memory leak that I mentioned to you earlier, where we allocate some memory and then forget to free it, it's really useful for that step of grooming the heap, because it's really important that there are no chunks in memory that are available to reuse. I need to be sure that when it allocates memory, it comes out of the top chunk in order to get a reliable exploit. So then I use the resizing chunks technique to create a chunk that overlaps with the top chunk. Then I use the local info leak in conjunction with the top chunk arithmetic technique to grab that stack pointer, subtract the offset from it, and then copy it to where I need it. Then I use the fastbin reverse into tcache technique to trigger the overwrite of the stack. And then as a result of that call to the TCP send, I receive that info leak, and then I'm able to send back my ROP chain, which gets copied onto the stack due to that behavior of the fastbin reverse into tcache technique. So let's take a look. I'm going to show you this in GDB, and I'm going to focus on that point in the exploit where it overwrites the value of buff size so that I get my remote info leak. Okay, let's just check that our my fake scanner is running. Okay, so it's starting to communicate there. So if we go back here, we should hit a breakpoint in a second. Okay, we've hit our breakpoint. Now I need to enable another breakpoint. Okay, so we're in net write, which is where the buff size value is going to get corrupted. So right here, let's see what buff size is. So it's 12 right now. I'm going to call malloc, and you see that now buff size has been overwritten with a pointer. So let's just enable some more breakpoints. So then we get down here, and you can see that buff size is that number. And if we look over here at the fake scanner, it's waiting for the stack dump. And so then if we step over that function, you can see that we've now received our remote info leak and some ASLR offsets, that sort of thing. Okay, and then let me just enable my final breakpoint. I need to skip that one. Okay, and so now we're in the net read function. The thing that you need to watch now is the stack frames in the bottom left window, because this is when the ROP chain is going to kick in. So that was reading the header. And then we come down here into the place where we read the ROP chain. And look, now the stack frames have been overwritten. And so our ROP chain is in place. And then if we continue, there's the calculator. Okay, so that was just about it. So sadly, it's time to say farewell to the House of Force. In fact, as soon as I've finished recording this presentation, I'm going to be upgrading my computer to Ubuntu 20.04, which is now the latest long-term release, long-term support version of Ubuntu. And it has glibc version 2.31, in which the House of Force is no longer viable. However, one thing that did occur to me after I finished writing this exploit is that maybe you can still do the top chunk arithmetic techniques, and maybe the House of Force isn't completely dead yet. So the change that's happened in glibc is they now check to make sure that the size of the top chunk isn't ridiculous. So if it's, say, bigger than 0.5 megabyte, then that will get detected and it will stop the program. But all I really needed to do was modify the final 2 bytes of the stack address. I needed to subtract an offset of, say, 300 bytes from that. And so those are stored in the final 2 bytes of the address. And so if, rather than copying the entire address into the size of the top chunk, I'd instead just grabbed the bottom 2 bytes and copied them into the size of the top chunk, applied the top chunk arithmetic technique to subtract my offset from that, and then taken those 2 bytes and then reconstructed my stack address from that, then I think that might have worked. It would have been a lot of work, but I think it might have been possible to do that. So one thing I did just want to mention is it does make me slightly sad that these checks keep getting added to the Malloc implementation. The glibc allocator is such a fundamental piece of software. It's used in so much of our software, and all of these checks are just making it ever so slightly slower every time they get added. And fundamentally, they're not stopping exploits from working. It just makes it more difficult to create a working exploit, but it doesn't stop it from happening altogether. And so it seems to me that the real problem is that there was a heap buffer overflow in the software that was calling the allocator. And that's the problem that needs to be fixed. It's not the glibc maintainer's fault that the allocator can be abused to get code execution once you've got a vulnerability like that. And so I think it's slightly sad that we keep adding more of these checks to the allocator. I would prefer if it was just lean and fast code and we focused on finding the vulnerabilities in the code that's using it in order to stop these kinds of exploits from being possible. So that's all I had to say. I hope you enjoyed it.